tunneling is one of those things. Quantum tunneling isn't like drilling a hole through a mountain, the way we think of with tunneling. In fact, it's something that only occurs in the quantum world, where a particle of some sort actually can be in two positions at one time. It's only when you actually look at it that you see where it really is. Well, any place that they're interested in what and how water molecules interact with matter or travel through matter, the fact that we have shown that a water molecule can, in and of itself, tunnel and move in that manner is going to affect how water as a whole can be transported.
Wouldn't it be nice to be everywhere at once? According to quantum mechanics, you are. At least a little bit. Quantum mechanics is a spectacularly weird theory. One of its basic tenets is that certain properties of an object are fundamentally uncertain. They don't hold well-defined values, but instead must be described as a distribution of possible states of being. Each specific state has a certain probability of being true when the object is observed. Or more accurately, until a quantum object interacts with something, all possible states are just as real as each other. Although not necessarily equally likely, there's a distribution of probabilities for each of an object's quantum properties. That distribution, and the way it changes over time, is coded in the object's wave function. The reduction of a fuzzy possibility space into a specific measurable property is sometimes referred to as the collapse of the wave function. We'll talk a lot more about this awesome weirdness in the future. For now, let's just look at the strange consequences of quantum uncertainty in an object's location. This is one of the early realizations in the development of quantum theory. French mathematician and physicist Louis de Broglie figured out that any material object is really a matter wave. It can be described as a wave packet of position probability, and that wave packet has a wavelength. This de Broglie wavelength defines how well determined an object position is. A large wavelength means a highly uncertain position. A small wavelength means a well-defined position. That's true of subatomic particles, and it's sort of true of anything. Right now, I'm mostly right here, but there's also a smaller chance that I'm here, here, or here. There's an infinitesimal chance that I'm on the moon. Observe me, and you'll collapse my wave function, and probably find me pretty much exactly where you expect to. See, an object's de Broglie wavelength depends on its momentum, so mass times velocity. Higher momentum means a smaller wavelength. In fact, it's the minuscule Planck constant divided by momentum. Humans are made up of several tens of kilograms of thermally moving particles and have de Broglie wavelengths a couple of orders of magnitude smaller than the Planck length. You're everywhere in the universe, but not very much. You're as right there as it's possible to be. But what about something much smaller? Say, a tightly bound bundle of 2 protons and 2 neutrons that we call an alpha particle.